Welcome faithful few, and I'm going to talk about continuity first. So that's the property of continuousness. So in your book it says that something is continuous at a particular point if the limit towards that point exists and is equal to the function value. So this is the actual definition. F is continuous at A if the limit as x approaches A of f of x is f of A. That's the definition of being continuous at a particular point. And it's continuous on an interval if it's continuous at every point in that interval. Okay? So, sorry about the fuzzy bit, that's actually a problem with the document camera. It's a fuzzy bit just there. So, what that means is a lot of stuff wrapped up in that definition, and there are actually 5 different things that need to happen for something to be continuous. And you need, if you want to check if something's continuous at a particular point, you need to run through all 5 of those things roughly in a particular order, and if any of them is wrong, at that point you stop and say it's not continuous. So these are the things that have to happen to make something continuous, which are actually listed in your book too. It says note, there are the 3 essential requirements. There's technically 5, so possibly even 6. So I'll know how many there are when I write them all. So the first thing that needs to happen is that the limit as x goes to A of f of x actually has to exist. Okay? And that's the first thing we're going to check. That limit has to exist, and if it doesn't exist, then the function is not continuous at that point. And in order for a limit to exist, you need 3 things to happen. You need the limit from one side to exist, the limit from the other side to exist, and for those 2 things to be equal. So that's 3 conditions all in one to give you that the limit exists. So we need. So what we need is we need the limit as x goes to A from below of f of x to exist. We need the limit as x goes to A. I'm probably not. Oh no, it's on. Okay, from above of f of x to exist. We need both of them to exist, and we need those 2 limits to be equal. That's technically 3 conditions. And in most places where you are worried about it not being continuous, you will need to check all 3. Now together, those 3 things together mean that the limit as x goes to A of f of x exists. Okay, so those 3 things together mean the limit of f goes to A of x goes to A of f of x exists. If any one of those 3 things are wrong and they don't work, then it's called an essential discontinuity. Okay, essential discontinuities are about the limit not existing. Okay, so just sort of in brackets, if any are wrong, that's an essential discontinuity. And essential does not start with the n. Okay, essential discontinuities are about the limit not existing. Yep?
I was reading the textbook. Is there different types of essential discontinuities?
Technically yes, but they don't mention them in your lecture notes, so we don't really care. Okay. So there are, because it's depending on the way that the limit doesn't exist. So there's the ones where if one of these 2 limits exist, you can don't exist, meaning it shoots off to infinity, it's sort of an infinite essential discontinuity. But if both of those exist but they happen to not be the same, it would be a finite discontinuity. Is that what the book said? Oh yeah, no. Finite jump discontinuity. That's not part of Maths 1B technically in terms of when they ask what to classify the discontinuity, they just want essential or removable. Yes. But I would point out that in engineering maths, if that's what you have to do at some point in the future, your lecturer will refer to an infinite essential discontinuity, assuming you know what it means. So, and then, so once your limit exists, there are two conditions left to go. You need the actual function value at that point to exist. And if that does exist, you need the limit to actually be equal to the function value. And if either of these two are wrong, it's called a removable discontinuity, because you've already checked these ones. Okay, so if all of these are okay, and one of these is wrong, it's a removable discontinuity. So if any of these two wrong, but the top three are right, that's a removable discontinuity. But of course, if all five of them are true, it's actually continuous. So if all five true, that means it's continuous. Continuous. Okay?
Does it also have to be differentiable?
No. You can be continuous without being differentiable. But if you're differentiable, then that implies you're continuous. So you have to be continuous in order to be differentiable, but you can be continuous without being differentiable, which I'll get to in just a second. I'll draw that. Remind me. No, I wouldn't have thought of it at the time. So remind me, and I'll draw you a picture and remind me at that point. So that really is the list of things you need to do to check to see if something is continuous at a particular point. Okay, so if there's any point that it's in doubt whether it's continuous at that spot, you need to run through all of these things in roughly that order. Okay, if you just want to tell if it's continuous or not, you can just check whichever one you think is best, the one that looks like it's going to be wrong first, and go, it's not continuous there. But it's almost always true that you're asked what kind of discontinuity it is, and the only way to know what kind it is to figure out the limit. Okay, so if you have to know whether it's continuous and what kind of discontinuity it is, you have to figure out the limit first and then do these things. Okay, and if any of these are wrong, you don't have to check these because it doesn't matter. Like if the limit doesn't exist, it's automatically not continuous and you don't have to check these two. Okay, it's really important. Lots of people don't, they say, oh, is it continuous? And I say, well, what should you check first? And they don't know. Now you know, you should check the limit first. Should I do an example of that, say? Before I go on to that, there's actually a few things that you know for certain must be continuous everywhere, and it's good to know those things, and I'm sure that there is a list somewhere. Yeah. There is a theorem, 4.1, the rules for continuity, which says that if you're going to combine functions together, then they'll be continuous in certain ways. So it says that if something's continuous, two things are continuous and you add them together, then the new thing will be continuous. Just here. If they were continuous and you multiply them, it'll still be continuous, but if you divide them, it'll be continuous unless the bottom is 0, in which case it will be discontinuous. So things that we know are continuous So things that we know are continuous are any polynomials, exponentials, something like that, e to the anything. You know, sine and cos. And, very important case, a rational function is continuous everywhere where its bottom isn't 0. So, f of x over g of x as long as the bottom's not 0. Okay, so basically, well, and as long as those two things were continuous to begin with, you know, everywhere. So, okay, so it's the sort of thing where you, when you get given a problem and you go, is this continuous, and you know, you discuss the continuity of this function, then you can look at it and go, well, here it's a polynomial, here it's a polynomial, here it's a rational function. They're all continuous. I only have to worry about the bits where the bottom is 0, basically. So places where that will be in doubt, you know, for a single function, places for a single function where it's in doubt will be places where the bottom isn't 0. Sorry, where it is there. Places where the denominator is equal to 0. It will most definitely be discontinuous there, because if the denominator is 0, it doesn't exist at that point. But you'll still have to do your limits to see whether it's an essential or removable. And anywhere where the function changes its definition. Okay, so if you've got one with a little brace, any point at which it stops being x squared plus 1 and starts being something else, that will be a place where the continuity is in doubt as well. Place where the formula changes. So you just need to write that down so that when I do my example, it will make sense the reason why I'm doing various things. So I wonder if I can find a good example that has, you know, most of those things in it. Yeah, I'll make one up. Don't write anything down yet until I've figured it out, because I'm trying to figure out an example that will make sense. So. Let's do that one. Okay. So this function, I'll just shift it up a bit so there's not a fuzzy bit. There we go. X squared minus 1 when x is less than or equal to 0, x plus 2 over x minus 2 between 0 and 4, and e to the x when x is greater than or equal to 4. Okay, so I know it will be continuous. Each of those particular things are on my list of continuous functions. That's a polynomial, it's continuous. That's a rational function, it'll be continuous except when x is 2. That's e to the x, that's always continuous. So the only places that I'm going to have trouble are places where the denominator is 0, which is when x is 2, and places where the function changes its formula. And it changes its formula at 0, and it changes its formula at 4. Okay, so I'm going to check x equals 0, x equals 2, and x equals 4 because those are my worry points. So it's continuous. Yeah. So this is continuous when x is not equal to 0 or 2 or 4. Basically because all of those, the formulas in those places are things that are continuous. Okay, based on my list of things that I know are continuous above. And you can just say that without giving a reason. That's perfectly reasonable. So then we're going to check each of those points separately. So we'll check x equals 0. So my list of things to do tell me that I should check the limits first. So the limit as x approaches 0 from below of f of x. When x is below 0, my function formula is x squared minus 1. And I can, therefore, because it's a polynomial, I can just sub that in, which is minus 1. Okay? And the limit as x approaches 0 from above of f of x. Well, the formula for f of x above 0 but close to 0 was x plus 2 over x minus 2. So I'm just looking at the bit that's right next to 0. And that's not 0 on the bottom, so I can just sub that in, which is minus 1. And now I check to see if they're equal, which they are. And so therefore, the limit as x goes to 0 of f of x is minus 1. Okay?
How come you didn't take it from above for x squared minus 1?
Because when I'm above 0, the formula isn't x squared minus 1.
Yeah.
So below 0, the formula is x squared minus 1, and above 0, the formula is x plus 2 over x minus 2. It's a very good question. Yes, if it was equal to that on both sides of 0, then I would have to use them separately. Okay. All right. So the limit exists. So if it's discontinuous, it'll be a removable discontinuity because the limit exists. It's not essential. Now I'm just going to check to see what f of 0 actually is. When x is equal to 0, that's this bit here, I'm going to use that formula because that works when x is equal to 0. So when f of 0 is 0 squared minus 1, which is minus 0, which is equal to the limit, so it's actually continuous when x is 0. So therefore, continuous at x equals 0. Technically, I should probably assert that this is actually equal to the limit. Okay, so it turns out that it's not discontinuous at that point. I was worried about it at x equals 0, but it's actually fine. No, next one I'll check x equals 2. So, I should check technically the limit from above and below separately, just in case. So the limit as x goes to 2 from below of f of x. Now in that zone where I'm close to 2, 2 is in this zone here, so the formula is x plus 2 over x minus 2. Okay, that's the formula when I'm close to 2 but below 2. And the limit of the top is 4 and the limit of the bottom is 0, so that limit doesn't exist. Because if the top is not 0 and the bottom is 0. So if you want to do the formal working, normally at this stage you just say dne, but if you want to do the formal working you actually have to do this. You would have to say, now the limit as x goes to 2 from below of x plus 2 equals 4, and the limit as x goes to 2 from below of x minus 2 is 0, so therefore the limit as x goes to 2 from below of x plus 2 over x minus 2 does not exist. But you don't have to do this bit, because mostly they'll just allow you to just stare at it and go, doesn't exist because the bottom's 0 and the top isn't. If the top and bottom are both 0, then I would have to do something else to see what it came out to. So I can stop now. I don't have to worry about anything at all because the limit doesn't exist. It's definitely discontinuous there. I don't have to do any more work. I can say there is an essential discontinuity when x is equal to 2. Therefore, at x equals 2. Okay? Good-o. And next I would check the next point. Check x equals 4. So the limit as x goes to 4 from below of f of x. Now below 4, the formula, so below 4 is this zone here. The formula was x plus 2 over x minus 2. So below 4, it's the limit as x goes to 4 from below of x plus 2 over x minus 2. And the bottom's not 0, so I can just sub that in, which is 3. And the limit as x goes to 4 from above of f of x. Above 4, the formula was e to the x, which is e to the 4, which is totally not 3. And so again, the limit fails to exist. So the limit as x goes to 4 of f of x without the plus or minus, just 4, does not exist because these two aren't equal. So we have another essential discontinuity. At x equals 4. So if they had said, here is a function, discuss the continuity, you would probably need to put a final answer in and say, so f of x is continuous for all x except x equals 2 with an essential discontinuity and x equals 4 with another essential discontinuity. Jolene, these are two different types of essential discontinuities. So one of them didn't exist because the denominator was 0, which means it has asymptotes at that point. And with the 4, it didn't exist because it did go to 2 places. They were just different places. So, but you're not supposed to be able to do, they don't care. So, but just so you know. Yes, so if at any stage, if this had existed and then I got to the next point and the function didn't exist at that point, then it would be removable. The classic is where they when they have this, they don't define it at x equals 4, or they don't define it at x equals 0, and they say it's like 7 when x is equal to 0. And you can go, limit exists, limit from above exists, limit from the bottom exists, they're both equal, so the total limit exists. And then you go, function value, the limit is -1, but the function value is 7. They don't match, so it's a removable discontinuity. So you work your way down the list, and if the top 3 are okay, then if it's a discontinuity, it's removable, and if the next 2 are okay, it's not a discontinuity at all, and it's continuous. So any more questions about discontinuity? Yep?
The 5th one in the list, I wasn't really sure about that condition. So how could that fail?
Exactly as I said then, I'll show you one. You have to actually set it up to fail to begin with. So it's usually fairly contrived. So just as another example, define f of x to be equal to sine x over x for x not equal to 0 and 3 for x equal to 0. Okay, this is a perfectly good function. It's sine x over x everywhere, except sine x over x is not technically defined when x is 0, so I just give it a definition when x is 0. So, by the same reasoning, it's going to be continuous everywhere where x isn't 0, because if x isn't 0, sine x and x are both continuous, and x isn't 0, so that's all fine. Based on our theorem 4.1, you don't have to give it a name, but it's definitely continuous when x is not 0, as the denominator is not 0. But our worry point is x is equal to 0, so we're going to check x equals 0. So we'll go, all right, the limit as x goes to 0, technically you would do the limit from above. If you can see straight up that the limit from above and the limit from below are going to be okay, you can skip that bit and do both of them in one go. Okay, so normally you do the limit from above, but we know that the limit of sine x over x does exist on both sides, so we can sort of skip that bit and just do the straight limit. Okay, so it is okay, see how I did this bit here. If you know that all of this is going to be okay because you've done it before, you can go straight to here and just do that. Okay, that's why I put them that way. So I can actually go, I know that the limit as x goes to 0 of sine x over x, regardless of the above or below, is going to come out to 1. Okay? So if I did the above, it would come out to 1. If I did the below, it would come out to 1, and that'd be equal, so the limit would be equal to 1. I can skip that if I know it's going to work. If you're not sure, then that's fine, and you can do all three. Okay, so if it's discontinuous, it will be a removable discontinuity because the limit exists. So, all right, so my limit's okay, it exists, and it's equal to 1. Now my function value at 0, when x is 0, the function value is 3, and that's not equal to the limit. So technically there should have been the limit as x goes to 0 of f of x. It's that. So since the function value is 3 and the limit is 1, they don't match up, and it's a discontinuity and it's a removable discontinuity. So yeah. It seems pretty contrived, but that's pretty much the only way to produce that last one, to contrive it. If I had chosen that to be 1 at that spot, it would have been continuous. If I had chosen that to be not defined at all and I just said it's that, then it would have been a removable as well, because you would have said f of 0 doesn't exist, because they haven't told me what it is. But in this case, they told me what f of 0 is, so I have to assert that it's not equal to the function value. So it's always fairly contrived to get that very last one. Okay. Now, so while we were in your lectures, there was continuity, and then they talked about the intermediate value theorem, and then you did differentiability. Oh, and the bisection method and Newton's method. Wow, awesome. And then you did differentiability. No, where's the differentiability bit? Is that earlier than continuity? Normally it's after. Have I missed some pages? Applied max and min problems. Oh, okay. Right, so you do the applied max and min problems before you do the general theorems about differentiability. Okay. Just making sure that I've got my ideas in the right order. Do they do the... I can't find a definition of... Oh, it's okay. It's before L'Hopital's rule. Okay. Right. So there's continuity, which is something that you can say about a function. You can say it's continuous at a particular spot. There is also differentiability, which is that you can say it's differentiable. And I should put that down because it's important. Which is a very long word. So something is differentiable. Definition: f is differentiable at A if the limit as h approaches 0 of f of x plus h, a plus h minus f of a over h exists. That's what differentiable means. Because this is the definition of what the derivative at that point means. That's the definition of the derivative, and it's differentiable if the derivative exists, basically. If it's not continuous, it can't possibly be differentiable. So there was a theorem which said that, and it went, if it's differentiable, then it must be continuous. Okay? But normally you think about it the other way around. If it's not continuous, it can't possibly be differentiable. So the concept that we have here is that if this is, all functions that are differentiable, that are continuous, then some of them are differentiable as well. Okay? So there are ones here that are continuous but not differentiable. For example, mod x is one of them. It's continuous. There's no jumps or gaps, but you can't differentiate it when x is 0. And then there are plenty that are, anything that, most things are differentiable that we care about. Okay? So there are things that are continuous but not differentiable. So, lovely. So if it's not continuous, if you see that there's a jump or a hole or a gap, you can automatically say it's not differentiable. So basically we've got not continuous means not differentiable. Basically. But if it's differentiable, that means it's continuous. But if it's continuous, if it is continuous, you don't know if it's differentiable or not. Okay? So you don't know, because there are plenty of ones that are continuous that aren't differentiable. So, as an example, you might go, is let me use the function I did before. I'll just cut it down a bit. Just that function. It's x squared minus 1 below 0. It's x plus 2 over x minus 2 above 0. And we showed earlier that that's actually continuous when x is 0. So, is f of x differentiable at x equals 0? Okay, so first you check. Actually, you know what? I'm just going to do exactly the same function because it's worth pointing it out. At x equals 0 or 4. So, back in the previous example, we figured out that it wasn't continuous when x was equal to 4, so it can't be differentiable. So we'll do x equals 4 first. It wasn't continuous at x equals 4, so it's not differentiable at x equals 4. And we can just stop. No need to do any more. But when x is equal to 0, it was continuous at x equals 0. Okay, so it is. So it might, it's possible that it might be differentiable there, but we can't tell without figuring out the limit, figuring out the derivative at that point. So we need to know what the derivative is at that point. Now it's a limit. So back here, technically what this means is that I need the limit as h goes to 0 from above, and the limit as h goes to 0 from below to both exist and be equal. So basically that means i.e. limit h goes to 0 from above, limit h goes to 0 from below exists, this exists, and they're equal. That's what I need to be true for it to be differentiable. So I'm going to have to do all three. And I really, really have to do both of these because my function is different on both sides of 0. Okay, it's got a different formula less than 0 than it does more than 0. So the limit as h goes to 0 from above of f of 0 plus h minus f of 0 over h. Okay, is the limit as h goes to 0 from above of f of h minus, now f of 0 was negative 1, because we figured that out earlier. Awesome. Now here's the thing, h is above 0, so I need to know what the formula is. So if I'm above 0, the formula for f is this. So what I actually get is the limit as h goes to 0 from above of h plus 2 over h minus 2 minus 1 over h. Woohoo! Now technically what this is asking me to do is do a derivative by first principles, but I know that x plus 2 over x minus 2, if I was looking at just that function defined everywhere, it would be perfectly well differentiable at that point because it's continuous, like it's a rational function. So this would be the same as the derivative of so I've got two choices now. I can either try and figure out what this limit comes to, which I do not like, or I could actually cheat. But, there's two ways. So I'll do the one with the limit first and I'll cheat with the other one to show you how they both work. It's not really cheating, you're allowed to do it. So with this one I'm supposed to the top has an h minus 2 on the bottom, so if I times both the top one and the bottom by h minus 2, I'll get h plus 2 over h minus 2 times h plus 2, and plus 1 times h minus, like that, which is the limit as h goes to 0 from above of, have I done that wrong? Yeah, that's fine. 2h over h minus 2, and then the h's cancel, which is good, they're supposed to do that. You're supposed to be able to get the h off the bottom. And now there's no h's on the bottom, so if I sub in 0, I'll get 2 over 0 minus 2, which is negative 1. Okay? So if the derivative is this, that's what it is. Okay, so I'm supposed to do the limit from above as well. So the limit as h goes to 0, from below, okay. Now, same thing's going to happen that happened before. I need to look at where h is. H is going to 0 from below, so h is actually negative. So when I'm below 0, my function, the definition of my function said that if I'm below 0, I should be using the formula x squared minus 1. Only it's h, not x. So what I should do because that's the formula. Now here's the really fancy tricky bit. The really fancy tricky bit goes, this is what I would do so if I did the derivative of x squared minus 1 by first principles. That's what I would do. Yep?
When you got, how you got on the first line f of 0 plus h, and
yep.
that that goes to f of h, the 0 like cancels out. There, yeah, that's 0. Is that not the function with 0 input into that function at x? Like, how do you cancel? Because if you put 0 into the function...
0 plus h is equal to h. No?
Oh, so you just add them together.
Yeah,
Oh.
so that is equal to that.
So
I haven't expanded it out. Yeah.
Alright.
And technically it is what you get if you put 0 into the function, but because you're dividing by 0 as well, you have to do it as a limit. So it might be that when you do the calculations, you have to do a cancellation on the top and bottom and it'll come out to a different answer. But it's worthy of note, that's a good point, that you see this is precisely what I would do if I was just differentiating 2x minus 1. It's like x squared minus 1. So this is actually the derivative of x squared minus 1 figured out at the point where x is 0. That's what it is. So technically I could have said that back there, but this is better because you're saying, well, this is the limit. Oh, and that happens to be the limit of, that happens to be the derivative of some other function. It has the same formula as mine, but it only has the same formula as mine when it's less than 0. So I can't tell it's the same until I get to this point, which would be what I get with 2x when I sub in x equals 0, which is 0. So that's the cheap version. I don't think they'd expect you to do all of this in an exam, but technically it does test limits as well. So, since the limit from above and the limit from below are not equal, so this is not equal to the answer we got before, which is minus 1, so f is not differentiable at x equals 0. You can tell a function isn't differentiable at a particular point if you look at the graph by noticing that there is a kink in it. This function so on this side it's x squared minus 1, which looks like this, because it's x squared shifted down by 1. And on the other side it's x plus 2 over x minus 2. Just give me a second. Awesome. So it comes to minus 1 and it has its asymptote at 2, doesn't it? And then when we're less than 2, it'll be negative. So it sort of goes down like that. Okay. So what's happening is it flattens out to 0 on this side, but it starts at being slopey on that side. So there's this kink, there's a sharp corner just there. So, just worth pointing out that any graph that has a kink will be not differentiable at that point. In particular, mod x or mod anything will be not differentiable at the places where it's equal to 0. So, that function there, this function looks like that, and the place where it turns is x equals minus 1. This function looks like that, and the place where it turns is x equals 3. So what this function is going to be like, so this is what this function looks like. Because it's mod x, which would be here, but shifted back 1. This function looks like this. Because it's mod x but shifted up 3. So if I add them together, oh, no clue. But it will have kinks at both of those spots. What happens? So over here, this one's positive. This one's negative. Oh, okay. Crap, got that wrong, didn't I? So I've got, no, that's fine. it'll look like that. So there's got these two kinks here. The slope on this side is negative something, the slope on this side is 0, the slope on this side is 0, the slope on this side is plus something, so it can't be differentiable at those places where it turns. So there was this computer assignment, right, and it said, you know, where is it differentiable? And you were supposed to just know it's the places where the mods are equal to 0. So it's continuous at those points though, because there's no holes here. The limit from this side is equal to the limit from this side, but this limit of the derivative, the limit of the slope isn't so equal. So yes. So your lecturer expects you to know that if there's a mod in it, it's going to have differentiable issues at the places where it's equal to 0. Right. Cool. So they're the main things I wanted to say about differentiability and continuity, unless, because there are other things in this topic, but they're the definitions of those things and how to cope with them. So has anyone got any questions about anything else that's near there, like intermediate value theorem or finding inflection points or any of that stuff? Yes?
There was something with the Rolle's theorem, and it was like, how can you use the Rolle's theorem to prove that this function has like no more than 2 zeros or something like that?
Yep. So, been asked by someone, just for the recording, about Rolle's theorem, and how to use Rolle's theorem to show that a function has a certain number of zeros. Yeah? Okay. So Rolle's theorem relates a function's derivative to its zeros. So let's see if we can find it. Okay. I just want to find the exact statement of Rolle's theorem. Rolle's theorem. Suppose f is continuous and differentiable on an interval, and if f of a equals f of b equals 0, then there is at least one c between them such that f dash c equals 0. Okay, so this is the actual theorem. If f is continuous on AB, differentiable on AB. That's a technical side note that you can be continuous on a closed interval, just saying you go up to that point and you can stop there. Technically you can't be continuous if it's not defined on the other side, but you can redefine continuity to say it's continuous up to A. You can't be differentiable if it's not defined over this side, because you need differentiability implies that there's a limit for the slope on both sides. So that's just a technical definition, that this one's a closed interval and that one's an open interval. It's not really that important, but that's why they do that. Then if f of A equals f of B, and they don't actually have to be 0, but they can be, then there exists a C between A and B such that f dash C equals 0. So it's saying if your function crosses any line twice, then somewhere in between the slope must be 0. It has to have a turning point. Which makes sense. If it crosses here and crosses here, it must turn somewhere in the middle. That's the concept behind it. Okay? Right. What that means is that if your function has a certain number of zeros, then you're guaranteed to have a certain number of zeros in the derivative. So that's the theorem. So, and usually you don't have to state this as a separate thing. They're happy for you to think of this as Rolle's theorem. If f of x has zeros, A1, A2, Oh no, just a second. Oh crap. I'll do it properly. If it has zeros at these points, yep.
Sorry, just quickly. Should you say fa equals fb and they both equal 0?
Technically yes, but actually no. You don't have to say they're equal to 0 if you don't want to.
Oh, okay.
The theorem in the book says equals 0, but you can still use Rolle's theorem if they're not equal to 0, as long as they're equal to each other.
Okay.
So they could be equal to 4, as long as they were both 4, Rolle's theorem would still work.
Oh, okay.
Because technically what you're doing is using Rolle's theorem on that function plus 4.
Yes.
So if it has zeros at those points, then f dash x has zeros between, in these intervals from a1 to a2, from a2 to a3, an minus 1 to an. Okay, so that's what it means. It's got, for every pair of zeros, you know that there's a zero of the derivative between them. So what that's basically saying, so if f of x has n zeros, that means that f dashed x has at least n minus 1 zeros. Because every pair of zeros that are next to each other gives you a zero of the derivative. So if there's n of them, there's n minus 1 spaces between them. So the concept in terms of a picture is saying that if your function crosses the axes at these, at those points there, so these are my zeros. So I've got a 0 of f of x here, 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 and a 0 of f of x here. Rolle's theorem, if you act Rolle's theorem just upon this bit, it says there's a 0 of the derivative here. So somewhere in the middle, f dashed equals 0. Somewhere in the middle of this one, f dashed equals 0. Somewhere in the middle of this one, f dashed equals 0. Somewhere in the middle of this one, f dashed equals 0. So what we've got is we've got 5 zeros of f, and that's telling us that there must be 4 zeros of f dashed. So n minus 1. Okay, you can do it backwards as well. So if you know that f dashed has, say, 4 zeros, that means that f can't have any more than 5, because if it had more, then f dash would have more than, would have 6, 5 or 6. So there's also if f of x, f dashed of x has sort of m zeros, that means that fx has at most m plus 1 zeros. Okay, so Rolle's theorem says that if you have a certain number of zeros in the derivative, then you can't have any more in the original function, or there would be more in the derivative. So every 1 0 of the original function that you add adds a 0 to the derivative as well. So think about what would have happened here if there was another 0, but So think about it. Suppose this is what you knew. You knew that there were 4 zeros here. If f had 6 zeros, then there'd be another orange dot here, and there'd be another 0 for f dash, and there'd be 5. But I know there's not 5, there's only 4. So, yeah. Yep?
When it refers to 0 in the differentiable 0, what does that refer to? Does that refer to like an inflection point?
Turning point.
Turning point.
So it's sort of like f dashed equals 0 here, f dashed equals 0 here, f dashed equals 0 here, f dashed equals 0 here. Yeah, because when the derivative is 0, that means there's a turning point in your function. Or well, it could be an inflection point, but there's definitely one where the derivative is 0 and it really is a turning point. Okay, so there could be an inflection point in here as well. There could be even more zeros in here, but they might be inflection points. There may be more local maximum and minimum. I can have 15 in here, but there's at least one. Okay, because it has to turn somewhere. It's like saying that something with an even power in it, like x to the 6, x to the 6 plus blah, 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 it has to have a turning point somewhere because this end points this way and this end points this way. Since both ends point the same way, there has to be a turning point somewhere in the middle. And it's the same idea. Both of these ends cross the x-axis, there must be a turning point in the middle. It could be down here, I can't tell. But yeah. So to see this, I wish there was a nice picture of this. And I'll do an example so you can, I'll try and think of an example. So just let me think about it. Yeah. I think this will work. I apologise if it turns to crap. Okay. So find the exact number of zeros of f dash x if f of x is equal to x squared x minus 1 x minus 2 plus 5. Maybe I'll just leave it without plus 5, just to make it less complicated, because that's probably what they'll do in the exam too. Okay, so note that I haven't been asked about the zeros of f, I've been asked about the zeros of f dashed, and usually it would say using Rolle's theorem. Okay, so this doesn't just use Rolle's theorem, it uses information about how polynomials' zeros work. Okay, so just because it says use Rolle's theorem, it doesn't mean it says use only Rolle's theorem. So it's not just Rolle's theorem that tells us about the zeros of a derivative, there are other things that tell us about the zeros of a derivative. Two useful pieces of information are that a polynomial of degree n can only have n zeros. Can't have any more than that. Could have less, could have none, but it can't have any more. So a cubic can only have 3 zeros. It could have 1 or 2 or 3. It can't have none. It could have 1 or 2 or 3, but it can't have 4. Okay, that's really important to know. Okay, and this f, it's a polynomial of degree 4. If I expand that out, I get an x to the 4 there. Okay, so that means that the derivative must be a polynomial of degree 3, because when I differentiate, I'll get 4x cubed, or whatever it is. Okay, so all of those things work together. So, but if I'm going to use Rolle's theorem, the first thing I need to know is about the zeros of f. So, the zeros of f are 0 and 1 and 2. Okay, it has 3 zeros. That means that according to Rolle's theorem, f dash must have 2 zeros at least. One between here and here, and one between here and here. So, therefore, f dash has zeros at least 2 zeros. It could have more. Rolle's theorem doesn't say it could have many as you like. Has at least 2 zeros. One between 0 and 1, and one between 1 and 2. Okay? Now that's all the information that Rolle's theorem tells us. It doesn't just tell us that it has at least 2 zeros, it tells us that there's one that's somewhere between 0 and 1, and there's one that's somewhere between 1 and 2. Okay, so far we know that f dash has at least 2 zeros, but we don't know how many zeros it has yet. It could have more than 2. So the next step is we need a way of narrowing down at the top. We know the minimum, we need to know how many it could have at the top. So more information is that f is a polynomial of degree 4. Therefore f dashed is a polynomial of degree 3. because when you differentiate a polynomial of degree 4, it comes down to have an x cubed in it because of the way differentiation works. All the powers go down by 1. So that means, therefore, f dashed has at most 3 zeros, which is distressing because we've now got at least 2 and at most 3. So our options are 2 or 3, and we haven't narrowed it down. In some special cases, you might have finished at this point and your function may have turned out to tell you that you had the right number of zeros. Okay, so if you had 4 zeros for f, that would give you 3 for f dashed, and then being a polynomial it has at most 3, so it must have exactly 3. But we don't have enough yet, so we need some other information that tells us one more, if we knew that there was one more zero of f dashed, we'd know how many there are, because we've got 2 already, and if we find a third one, that must be all of them, because there can't be any more than 3. So there must be even more information that we can get, and it's to do with this squared here. Okay? Let's not quite find the derivative of f. Let's call the other bit of f, let's call it g. It's got x squared and the x minus 1, x minus 2. I'll just call that g, because then if I use the product rule, I can differentiate this bit, I can keep this bit and differentiate the other bit, and look, they've both got an x in them. So that means that f dashed of 0 is 0. So I've found another 0 of f dashed. I know it's different to the ones I had before because there was a 0 between 0 and 1, and that means since it's strictly between 0 and 1, there's a 0 that's not equal to 0. So the previous zeros were between 0 and 1 and 1 and 2. So this is a new one. So therefore f dashed has 3 zeros. Yep?
In one of the lecture examples, you also use the intermediate value here.
Yes? I'll do another one like that. Okay, so what we've done in this example is we've used f, and information about f, to tell me about the zeros of f dashed. You can work the other way and use f dash to tell you about the zeros of f. So I'll just think of one. Okay. All right. Yep.
Do you have to say what the values of the zeros are?
No, because we don't know what they are. Because, now if they said, what are the zeros of f dash, the quickest way would be to just differentiate it and find what the zeros are. But they specifically in that other question said, how many zeros does it have? So what we've done is we've used Rolle's theorem to tell us how many it has without actually finding what they are. We found one of them 0, but we know there's one between 0 and 1, and there's another one between 1 and 2, but they haven't asked us to find them, so we'll just leave it at that. Okay, so find the number of zeros of tan x plus x, using Rolle's theorem. Okay. All right, well, again, they haven't asked me to find the zeros, though presumably x equals 0 would do the trick. They've just asked me to find how many zeros it has. Now, Rolle's theorem relates the zeros of f to the zeros of its derivative. So if I'm going to use Rolle's theorem, I should differentiate it to see what I get. derivative of tan is sec squared, derivative of x is 1. This function has no zeros. Okay? This is positive. This is greater than or equal to 0. So this whole thing is greater than or equal to 1. It's never 0. So therefore f dash x is greater than or equal to 1. So it has no zeros. So let's think about this. If f had 2 zeros, Rolle's theorem would tell you that there would be a 0 of f dash between them. So f can't have 2 zeros because there would then be zeros of f dash, and f dash doesn't have any. So run that way. If f had at least 2 zeros, then f dash would have a 0 somewhere between those two. By Rolle's theorem. But f dash doesn't have any zeros. So since it doesn't have any, f can't have 2. Okay? It's a proof by contradiction, basically. So therefore, f cannot have 2 zeros. If it did, f dash would have zeros, and it doesn't have any. So f has at most 1 0. Yep? So number of zeros for f is less than or equal to 1. Awesome. So either f has no zeros at all, or it has exactly 1 0. So I've got two options. I can either go, well, look, if I put x equals 0 in, ta-da, there's a 0. I found 1, it has 1, therefore that's all it has. But what I might do is I might go back and adjust this to be like, so that I can't just think of a 0. Okay? Hopefully I haven't destroyed it now. So, if x is quite close to 0, pi on 2, say. Tan has an asymptote at pi on 2, which means that tan can be as big as I want. So at this stage, to figure out how many zeros it has, I need to just figure out what f of various things is until I figure it out. So we're just going to try values of x for a while. F of 0 is tan of 0 plus 3, which is 3. If I can find one where it will come out to be negative, then it will be positive somewhere and negative somewhere else. And as long as it's continuous between those 2 points, then it will have to have a 0 between them. That's what the intermediate value theorem says. The intermediate value theorem says that if it's above the x-axis somewhere and below the x-axis somewhere, it must cross the x-axis somewhere in between, as long as it's continuous in that spot. So if I can find another point where it's negative, I'll be really good. So do not like it. That's awful. Minus. What does tan look like? Just a second. So we've got tan, which looks like that. We're adding 3 to it, which means it looks like that. And we're adding x to it, so it's going to be like worse. And the issue is going to happen here at minus pi on 2. So it's going to be negative over here somewhere. So I'm thinking if I pick something like minus, what's pi on 2? A minus 1 maybe? And see what I get? Just guessing. Maybe minus 1.3. What's tan of minus 1, people? Minus 1 is in radians.
Minus 1.5.
Not quite big enough? Alright. So this is still positive, is it? Okay.
Only just though.
Oh, maybe we'll choose 1.2 then. So what's tan of minus, what's that come out to? Tan of minus 1.2 minus 1.2 plus 3.
Minus 0.7.
Minus 0.7. Okay. So it's a bit of trial and error